Welcome everybody. This webinar is going to be recorded and will be shared after the webinar in digital platforms from HDF Group and from Hermes websites. So first of all, welcome everybody. I'm Anthony Kugas from Illinois Institute of Technology. And I'm happy to be here to present to you some of the latest developments in our system, Hermes, which is a distributed buffering system. So we have prepared a really nice agenda for you today. We're going to have a little bit of a project overview. I'll go over very quickly from an architecture like a recap, and then we're going to present the latest developments in Hermes, which is the buffer organizer. We do have some results and some presentation like demos and things like that. We will close with future work and some time for questions and answers. So let me start by introducing the project itself. Hermes is a collaborative project funded by NSF between the Illinois Institute of Technology, the HDF Group, and the University of Illinois at Urbana-Champaign. We're very happy and thankful to the NSF for funding this project. So I'll start with the what is it, what's the problem statement, what's the area we're working on. Traditionally, memory systems and storage demonstrate wildly different performance in terms of latency or bandwidth and data representation. Applications experience performance degradation due to slow remote access to storage. So there's an I/O performance gap between a typical parallel file system, usually based on disks, and in-memory subsystems. So a lot of modern storage system designs include multiple tiers of storage organized in a deep distributed storage hierarchy. The goal is to mask the I/O gap between memory and disks. Each system, however, is independently designed, deployed, and managed, making it very difficult to reap the benefits of the hierarchy. As you can see in the slide, like there's a bunch of different technologies and software associated with the hardware deployments, different file systems optimized for different mediums, and it's a little the landscape is quite complicated for the end user to be able to deploy and mount and utilize all these extra storage tiers. So ideally, the presence of multiple tiers of storage should be transparent to applications without having to sacrifice I/O performance. So here, this is the area that we aim to help with this new distributed multi-tier buffering system called Hermes. Hermes wants to abstract all of those tiers and just provide you a simple buffering layer where all the tiers and all the movements within the tiers are handled by the library. So in highlight, it enables and manages and supervises I/O operations in the deep distributed storage hierarchy. Hermes is not a storage system, it's a buffering system, so it doesn't really change anything to your typical application. It's transparent. You just link to Hermes, you buffer in Hermes, and then you can instruct Hermes to say, I want my data to be flushed out or written permanently in your backends. It offers a selective and dynamic layer data placement. It's modular, extensible, and we are mostly performance oriented. And we want to support a wide variety of applications, including scientific computations and big data. In terms of the ecosystem, it's a collection of different you could say like plugins or modules. The first and foremost important is the Hermes core library. That's the main thing that manages tiers transparently and facilitates data movement in the hierarchy. We have developed and we are welcoming the community to develop even more adapters. And I'll say a little more things about the adapter layer, but so far we have a POSIX, a standard IO, an MPI IO, and a PubSub adapter where the applications doesn't have to change anything. You just link to Hermes. There's a POSIX adapter. We capture the IO and we send that to the native API down to Hermes. We do have a Hermes virtual file driver for the HDF library, which makes it very easy for the end user to use. You just have your library, you set your VFT to Hermes, and then all your IO is going to be buffered into Hermes without any difficulty. We also working on a vol, and the vol it's a virtual object layer. So we want to capture high level representations or access patterns and statistics from the HDF5 API, and then communicate those things down to the Hermes library for further optimizations. If we know what you're gonna do, let's say reading, and we can kick in the prefetching within Hermes to accelerate read operations. And finally, there are some additional tools outside of the Hermes library, So the architecture, very high level and very quick to recap for people who are new here or they've never seen this project before. This is the core library, has a bunch of components. Today, actually, do I have a mouse? I do have a mouse. I don't know if you see the mouse, but we're gonna be releasing this soon, like today or the next week, the buffer organizer here. But there's a lot of interesting things here. The API is very simple. We follow an object store kind of API with puts and gets. There's a data placement engine that's responsible to place incoming data into the hierarchy and fully like distributed and tiered. And then there's internal components like the buffer pool manager that does the allocation of buffers across the hierarchy, manages the buffer IDs and all of these things, metadata management and things like that. We do have a collection of IO clients that they can be hooked into, RAM tiers, NVMe tiers, PMEM tiers, best buffers, and all kinds of different layers outside of Hermes. So the adapter layer, as I said, we want to make easy for users to plug in Hermes into the workflows. That's why the adapter layer, I think it's pretty critical to the adoption. But the most power, I mean, as it's the truth for any software out there, it's the native API. You can do a lot of things. But again, the adapters are there to help. Okay, a little bit about the data model, just for you to understand what is, the terminologies and the model we have. So maybe in the buffer organizer, you won't be a lot of, lost. So everything in Hermes starts with like a blob. A blob is a unit of data. And it's a key value. It presents itself as a key value pair. The values, they're an interpreted byte array, and it's stored internally as a collection of buffers across multiple tiers. So a blob, in a way, has a composition. It can have a collection of buffers, maybe a couple of buffers in memory, a couple of buffers in NVMe, all of them together, they're presented to the user as a blob. The user just pushes the blob or reads the blob, puts and gets the blob. A collection of blobs can be placed in a bucket. It's just a flat blob organization. You have a bunch of blobs. You wanna organize them in a collection. That's your bucket. Additional to that, we have the concept of a virtual bucket where you can link blobs across multiple buckets. And it just again, it's another construct for us that allows us to do additional capabilities. Like in a B bucket, you can link a bunch of blobs across different buckets, and you can attach a capability we call trait. That trait can be simple as, I want to put all of those blobs into this virtual bucket and apply compression. Or I want to put all of these things into this virtual bucket and instruct Hermes never to evict these blobs from memory. Okay, that's like a special capability, right? And then you can do that across multiple buckets. Traits can be a lot of things, like an ordering trait. I want you to keep them in order, or a grouping, or a filtering, and all kinds of different things. We do have already implemented a collection of them, but again, this can be also user driven. If you have a particular operation, you can code that and put it as a trait into your code. Okay, a few things about the project. Again, how can you get involved? We would love the community to be involved. We're looking for people, applications people, developers, anybody who's interested in this space. The GitHub repo is on the slide. Please, feel free to use it. You feel free to create, an issue for a feature request, for a bug, or for whatever it is. It's still under heavy development, and you're welcome to join us on the forum for any conversations or any other things. Okay, cool. So that's the project. That's the main architecture of the project. Let's talk a little bit about the buffer organizer. Why is it important? Why do we have it? And what's the main objectives? So, a little bit of a simple observation, which to many of you may be very clear and very straightforward. The way you write things is obviously not always the same as you read things. And especially in an environment where you have multiple tiers of storage and multiple nodes and content being written in Hermes, being distributed everywhere, and also vertically and horizontally, like everywhere in this space, it means every blob will be injected in the space, but it won't be always there in that location. So how you read it might be affecting where the blob is moving inside the hierarchy. So we do have this model, a predictor corrector model, where we have the data placement engine making near optimal, I'll say, as much as possible optimal decisions to place content into the hierarchy. And then we have the buffer organizer kicking in asynchronously in the background, trying to reorganize buffers and move around blobs to the appropriate locations. That can be a simple scenario. For instance, you have a checkpoint application, everything is writing. You want to make sure upper tiers of the hierarchy have enough capacity to accept incoming IO as quickly as possible. So what we do here is like the buffer organizer will start checking the upper tiers of the hierarchy and start moving blobs previously written to the bottom parts of the hierarchy. Again, the bottom parts of the hierarchy might be devices that they're more dense, they have more capacity, but they may have less bandwidth and higher latency to access. But again, it depends. So this buffer organizer, in summary, has a couple of responsibilities. First, it's the management of the hierarchical buffering space. In this context, we're really referring to how do we flash things, from upper tiers to bottom tiers? Do we pipeline content down? Do we, forward things across tiers and things like that? So that's his responsibility. It's responsibility. Another thing is read acceleration. Again, maybe some of your blobs are resting in a bottom part of the hierarchy, and then you want to kick in an analytics job or a consuming job of this content, where buffer organizer will try to elevate those blobs from the bottom parts of the hierarchy to the upper parts of the hierarchy. How does it do that? Chris can tell us more in a minute, but in principle, we have a scoring scheme that tries to score blobs inside Hermes based on how hot these things are. Hotness is a function. It can have a lot of variables there, like the frequency of access, the recency of access, sequentiality of blobs, like do they belong together, locality, different things like that. But we aim to capture that hotness and naturally allow the buffer organizer to move content that's hot into the upper tiers without the user having to be involved in that. Second one, the buffer organizer will manage the data life cycle of the content of the blobs. So as I said earlier, when is the blob in equilibrium? Like once you write it, should we leave it there and forget about it? Or does the blob, move in the hierarchy, both like vertically up and down the tiers and horizontally based on who is requesting access to that? Like, so that's again, with an objective, of course, to eliminate unnecessary movements, right? Because this equilibrium means the buffer organizer won't always move things around, right? So we had to have a lot of control over these things inside the implementation. So that's the buffer organizer objectives. I will give the floor to Chris Hogan, our lead engineer on the project. And with that, Chris, the floor is yours.
Okay, thank you, Anthony.
Should you present maybe your screen, or should you want me to be moving the slides forward?
I'll present.
Okay, let me stop here and then Chris will present. Stop sharing. All right, perfect.
Okay. Okay, I'm Chris Hogan. I'm a software engineer with the HDF Group, and I'm going to show you some how the buffer organizer works, why we need it, what it can do, and some results. So to get started, I like to choose just simple examples to make it really easy to understand. So our motivation here is just an example of an app that's doing checkpointing. So a very write-heavy phase. So think of it like heavy compute phase and then heavy write phase. Uh, and also I'm imagining we are using an adapter, so we're intercepting IO from an existing application that's doing this checkpointing. And what will happen is Hermes will intercept those writes and start redirecting that data to the hierarchy. Um, and in a write-heavy case, you would use a data placement policy that goes to the most capable tiers first. So it will start writing to RAM to get the fastest bandwidth, and then spill over to NVMe, and finally burst buffer. This is the hierarchy we're working with. So after a while, after some writing, your first two tiers will fill up. So this is the status we have now. Hermes, RAM, and NVMe tiers are full, and your burst buffer tier is completely empty. So at this point, all future writes will just go to the burst buffer, and you'll essentially get the worst performance. It's the worst case scenario in Hermes for this application. On the other hand, if you're in this state, this is great for reading because all your reads will be from the fastest tiers. But for writing, what we're talking about here, this is the worst state you can be in. But I will say, even though this is the worst state for Hermes, it's still better than not having Hermes at all, because in that case, you would be going to the PFS. Whereas here, at least we're getting burst buffer speeds, which should beat the PFS. So what can we do about this? What's the solution to this problem? Well, ideally, we would be, as these incoming writes fill up our RAM and NVMe tiers, ideally we would have a background process, which is the Borg, migrating data out of those tiers and pushing it down to the lower tiers, thereby freeing up space in fast tiers so that incoming writes get faster bandwidth. And that's exactly what the Borg does. Make space in higher tiers by moving data to slower tiers in this write-heavy case. So the next question is, how do we decide which data to evict or kick down to lower tiers? And that's where the scoring comes in that Anthony mentioned. We have a concept of importance scores for each blob. And we track those based on recency, frequency, and some other elements. And so the least important data gets evicted first from the most capable tiers. And now, assuming you have enough enough compute, you can kind of, this is all this IO is asynchronous. So assuming you have some compute that can overlap, the board can be a background moving things down, making space while your application is writing to these fast tiers, and everyone's happy. And here are some results of an application that does exactly that. The blue line is without the buffer organizer. And what I've set up here is a hierarchy where I'm doing 2,000 puts, and the first 1,000 puts basically can fit in the RAM and NVMe tiers. And the second 1,000 puts have to go to burst buffer. And we see the first 1,000 puts getting RAM speeds, and as soon as those two top tiers are full, we drop down and we get burst buffer speeds the rest of the way. Interestingly, in this case, NVMe speeds are RAM speeds because of the page cache. Essentially, assuming you have enough memory for caching, all your writes just get cached. So that's basically RAM speed. So that's why NVMe looks as high as RAM. But if you have memory pressure, NVMe will drop down a little bit because it'll have to flush immediately. So the red line is when we introduce the Borg. First, you'll notice that the the high bandwidth of the Borg is a little bit less than the highest possible bandwidth without the Borg. That little gap just represents the overhead of adding extra threads to do this movement, calculating which blobs to evict, and keeping track of scores and all that. So there is a little overhead, but you see that in this case it's worth it, 1.7x speed up. And the Borg, the capabilities of the Borg manifests itself a couple ways in this graph. First, you'll see that the blue line trails off around after 900 puts, but with the Borg, it's able to get a few hundred more puts in there, because while it's operating here, it's making space in RAM, so we get a little bit more extended top speed. Then we finally do fill up completely and we drop down to burst buffer speeds. But as we're doing this I/O to the burst buffer, the buffer organizer is in the background, constantly moving things down, just like this. And so once space gets cleared up, we get these bumps where it's like back to closer to RAM speeds, like heartbeats here, spikes and bandwidth. So we spike back up here and then we fill up the RAM and NVMe, and then we spike back down to burst buffer. Buffer organizer makes some more room, and we spike back up and down. So to show this behavior, I'm looking at the average bandwidth for every 30 puts, because I expected to see these spikes, and that's exactly what we see. But if we, rather than looking at this average bandwidth, we can look at total throughput. And also, this is just one rank. So I looked at total throughput, and I scaled up on a single node to saturate all the cores on this node, 40 in this case. There's one buffer organizer per node. So in general, I mean, you can do, other nodes can call buffer organizers on other nodes, but in general, a buffer organizer needs to support as many ranks as a single node can support. And so in this case, you can see we get 4x speed up. And once we get up here, the buffer organizer is using 8 threads in this example, so the machine is a little bit oversubscribed. But in general, we get a 4x speed up when we are using all the ranks on a single node with the buffer organizer. So pretty cool. Now let's look at the opposite example. Rather than a write-heavy example, let's look at a read-heavy example. For this, let's pretend we've been running an application for a while, and somehow we end up in a state like this, where RAM is empty, NVMe is empty, but our burst buffer is full. This could happen in several ways. Maybe you'd open several files and then you close some files that you didn't need. So those files happen to be up here. However you get here, let's pretend you get here, because this is the worst case scenario for reads. This is the best case scenario for writes, because you get maximum write bandwidth, but for reads, worst case scenario. And again, I'll say, even though it's the worst case scenario, it still beats going straight to the PFS, because you're reading from burst buffer. So what can the buffer organizer do in this situation? Well, it's essentially the same thing, just in the opposite way. Take data from the slowest tiers and move it up to the higher tiers. And again, which data do we choose? We choose based on that importance score. So the most important data should belong up in the higher tiers. This doesn't, it's a little different from the write case, because with writes, all we care about is free space. But with reads, we care about having the data we're about to read up here. And that's where prefetching comes in, which will be a future webinar. That's what we'll be working on next. So right now the Borg isn't perfect in this case, because even though you have your important blobs up here, there's nothing to say that an application might want to read, something that's still considered unimportant by Hermes, but that the application chooses to read. we'll start to solve that problem with prefetching. But in this case, most of your data will be moved up, so the majority of your reads will be faster. And here are the results for this style of application. Without the Borg, we get basically just burst buffer bandwidth. And these are small writes, so that's why it's not so great. Also, I think this is a single rank doing 32 kilobyte writes. So pretty slow just with the burst buffer, but we turn the Borg on, and the Borg is in the background, constantly moving data up to fill these higher tiers, and so the reads are getting RAM and NVMe bandwidths. And again here, the more compute that you can overlap, all the time you're computing, you're giving the Borg more time to do this data transfer. So essentially, the more compute you have, the closer this number here will approach RAM bandwidth, assuming you can fit however much you can fit in there. In this case, again, it's half my data can fit in NVMe and RAM and the other half in burst buffer. So if I take everything from burst buffer and put it in NVMe and RAM, it can all fit in this example. So this should be twice as fast. I'm still working on closing some performance gaps, but right now it's a 32x speed up with the Borg, which is really cool. All with no code changes to your application. Okay, so that's read heavy, that's write heavy. Those are the obvious cases, the easy cases. What about everything else? Every other application in between? Mixed workloads, and how can a user, what kind of control does a user have over this component? Well, we provide an option in the configuration file called BO capacity thresholds. And this gives you a set of values for each tier. So for example, here I have a set of values for a pair of values for the RAM tier, pair of values for NVMe, and a pair of values for the burst buffer tier. And then for each pair, we have a minimum and maximum capacity threshold. What does that mean? Basically, the minimum capacity threshold, you're telling the buffer organizer, hey, keep this tier full at least, in this case, 80%. So here on this one, I have 80.8 as the minimum threshold. That's saying I want RAM to be at least 80% full all the time, because I have a read heavy workload and I don't want my RAM empty while my burst buffer is full. So keep RAM 80% full at all times. That's the minimum capacity threshold. The maximum capacity threshold is the opposite. So for a write heavy case, you would want a high maximum, or a maximum threshold less than 1, which would be 100%. So this is saying if my RAM goes above 70% capacity, then start moving things out. It's saying keep available space open in RAM, because I know I have a lot of writes incoming. So that's the min and max thresholds. So to completely disable the buffer organizer, you set the minimum at 0 and the maximum at 1, because you'll never move anything below 0% capacity, and you can't fill anything beyond 100% maximum capacity. And then anywhere in between is where you can attempt to tune the buffer organizer's behavior to your application. So these are the examples that I used for the 2 demos that I showed. For a write heavy, we don't care about minimum capacity, because we want to max out we care about maximum capacity for the high tiers, because we want to this is saying keeping 30% available. When RAM fills beyond 70%, flush things out. So you essentially are always trying to save 30% space in RAM for incoming IO. Same with NVMe. And then for read heavy, we're saying I want my RAM to always be at least 80% full. So RAM should never go below 80% capacity, because I know I'm going to be reading a lot. So once RAM goes below 80% capacity, that's when the buffer organizer starts kicking things up to try to fill it past that 80%. And you can also configure the number of threads that the buffer organizer uses. So if you know that you have a workload that will require a lot of data movement, you can give it more threads. And if you know that you don't need that much data movement, you can cut it down a little bit. So this is the user-facing behavior. There is some system-side behavior where every so often Hermes checks in with other nodes and looks at the state of the hierarchy to see what the current capacity is, and it has to update the kind of a global metadata thing so that everyone, every epoch, everyone has to kind of sync on what the capacity is. And at that point, the system can look at internal buffer blob scores and look at the importance of those scores and compare that to like the current access time of like how fast would it be to read. So if you have a blob that's like importance 100, but it's in burst buffer, its access time is really low. So internally in the system, we're always trying to bring those two things together. That all happens in the background. So the only thing the user can do to control that is you can actually set the interval at which that is checked. So just to show that we're doing things in the background, but you can also do have some control over things. Okay, so that's the buffer organizer, and now I'll talk a little bit about what our next steps are in the roadmap in the coming few months. So the Borg is basically done. I'm closing just a couple small performance gaps right now, and once that's finished, I will merge it and release version 0.8.0 beta of Hermes. So as soon as you see this 0.80 released on the Hermes repo, which is here, then the Borg will be in there. Hermes is currently beta software. We are working on a monthly release schedule, and we tend to alternate bug fix releases with feature releases. This release will be the buffer organizer, and then we have a few activities to complete before we release our first major version, 1.0. Stage in, stage out workloads. These are jobs that can happen before your main application, before or after your main application runs. So stage all your data in from parallel file system into Hermes, start your application, read from fast buffering, end your application, and then Hermes moves everything out, that kind of thing. Prefetching, which I already mentioned, that will be in the next feature release. And then we're working on real applications on real machines. So that's what we're looking at for the next few months, and we're hoping for version 1.0 around October. GitHub repo is here, and all the documentation is in the Hermes wiki. And the best place to start is this Getting Started guide, which walks you through an example of using the adapters with IOR. That's it. I think we can take questions now before we go into the FAQ.
Thank you, Chris. That was amazing. Yeah, before we continue or we wrap up, do we have any questions? Let's monitor the chat, or if you have any live questions.
I have a question.
Mm-hmm.
So what I'm getting from this is that you can link Hermes into an existing application, and it will intercept the calls and just do this tiered buffering for you. Is that correct?
Correct.
Okay. What do you need to do in terms of setting up your infrastructure to make use of this?
Good question. If I understand, you're asking more about the deployment kind of models we have.
Yeah.
There are a couple of them. So one is you just connect the application with Hermes, and Hermes is tightly coupled to the lifetime of the application. So the application starts, think of like an MPI init. We intercept that, we launch Hermes, we launch some sort of processes in the background for every node, the Hermes core, we call it, that may have, a few threads or whatever, but that's the initialization phase. The program continues, executes, does all the IO, the buffering. At MPI finalize, we wrap up, we do whatever we need to do to clean up the Hermes deployment, evicting content out and killing processes and things like that. And then we exit with the application. The second mode is what we call usually a Hermes daemon mode, where you can just launch Hermes on your allocation. Say the scientist came, he got like 100 compute nodes and a couple of IO nodes for, I don't know, buffering or whatever. Deployments like best buffers or shared IO nodes with fast flash storage or something like that. Then you get the allocation. The user is responsible to get the allocation from the global job scheduler or something, knows the nodes, launches Hermes on those allocated nodes. Before the program starts, Hermes is there up and running, waiting for the program. The program arrives, again, during initialization, connects to Hermes daemons, does a lot of IO, the program exits, Hermes is still there. Content is still there, data is still there until you kill it manually, right? If you have a workflow, for instance, that's a great scenario because you can have producer-consumer stages of your workflow, and then you have Hermes daemons running the entirety of the workflow. And therefore, you don't really need to manage, movements between instances of Hermes or things like that. So you launch daemons, your producer programs write buffer data into Hermes, the consumer programs read out of Hermes. After the whole workflow executes, you just kill the instance. Of course, the content is on user. If the user wants us to evict and flash permanently content out of Hermes, we can do that. If the user doesn't care because he used Hermes as a temporary scratch space, the content will be deleted. So that's all like clear semantics provided by the library and the user. So these are like a couple of ways you can deploy Hermes. I hope I answered your question. Okay. We have a question from the chat. If I knew how much write IO, say in size, I have per node, how to figure out the percentage of Borg, the min and max, so I can get near RAM performance for all IO? Fantastic question. Why don't you start playing with it? Run your jobs and let us know what was the percentage. Again, it's very workload specific. Since we are actually doing now more testing and more application-driven deployments and scalability tests, and even the buffer organizer, we'll have a little more intuition, more like rule of thumb, how to properly configure these things. I know it's not really an answer, but it is what it is. We learn as we go, right? Like every major software is like that. So please use Hermes. Let us know your experience. Where did we mess things up? We can fix it. Another question from the chat: are data able to be reconciled with permanent storage systems like PFS? Yes. Couple of ways, right? So if you're saying everything should be transparent, I don't even know that the Hermes exists in between my application and my parallel file system. So let's start by default. By default, you have your application, say it's an HDF5 application, it produces HDF5 files, and the output of all of that ends up in the parallel file system in the form of HDF5 files or whatever, POSIX files or whatever you have, right? If you connect Hermes into this, as you maybe understood from the presentation, we will intercept all of this IO, we'll buffer all of these things into Hermes. At that stage, there is no HDF5 files because everything is buffered in Hermes, and Hermes has a different data model with buckets and blobs and everything. At the end, let's say you close a file or you close your data set or you finalize your job or whatever it is, through the configuration of Hermes, you're instructing Hermes to say, go and reconstruct the original HDF file I wanted to write in the parallel file system. And therefore, all these buffers and all these blobs are going to go back to the HDF file on the parallel file system. I hope I answered the question. Fantastic. Any other question? We'll be welcoming any kind of question. I do have some pre-prepared questions. Again, it's kind of things that we heard from community and from friends and friends of Hermes in a way. One question we have is like the integration in the HPC environment, a little bit of the deployment models earlier the question. I think I kind of answered that, but ideally, what we would like to see in a way, or the vision is that system administrators should also be a little bit involved in that. Users they're not always an IO expert, and they don't always know everything to get the resources and allocate everything. So in combination with a scheduling layer that kind of allocates buffering resources, and I call buffering resources very loosely, that could be the RAM, some percentage of RAM allowed by the user to be used as buffering space. You can set it to 0, like no one forces you to use RAM. But if you have a data intensive job, if you provide some RAM available, say 20% of every node is available to Hermes for buffering operations. These are the things that we would like to kind of solidify moving forward, like getting the NVMEs on the compute nodes. I mean, we can manage that. Like the Hermes library will mount it and will use the NVMe drives, and all the buffers are going to be allocated into the drives or SSDs or whatever you have. But a little bit of a coordination or co-scheduling with the global job scheduler is a fruitful area of research for this space where management of resources and Hermes as the software that manages all of that is coordinated with the scheduling layers. Other questions, some sort of dependencies. We try to keep dependencies for the software very minimal, but we do have some. We're using Thallium, a RPC library for high performance computing. We do use glog, the Google logging library. MPI, it's supported for MPitch and OpenMPI release implementations. The CATS2 testing framework is also used if you want it. And you can learn more, of course, on the GitHub repository on README.
It's also in the official SPAC repo now. So
yes,
if your
great.
SPAC is new enough, SPAC install Hermes should work.
Great. That's a very good comment, Chris. You're right. Like we did work with SPAC, and now it's officially in the SPAC modules. And if you have availability on that, very easy, SPAC install Hermes, and everything else should be working fine. We did play a little bit with Docker images for like quick and easy deployments for testing and playing with Hermes and see what's it about. So we do have that as well. But I don't know how many HPC sites have like Docker and things like that. But again, how to start with Hermes? Again, do I need to make changes to my applications? No, there's the adapter layer, no code changes, LD preload, and it should work. Just reminder, POSIX, standard IO, MPI IO. We did work on a publish subscribe because a lot of maybe streaming applications that just want to publish content into Hermes, and that library is capturing that pubs up models and intercepts that and pushes it down to the native API. And I think the HDF5 workloads should be very happy. We're partners with HDF Group, and Hermes, from the scratch wanted to be playing, well with the HDF5 library. So the HDF5 VFT layers and the vaults and all of these things should be helpful for the community. Other things, I don't know. Do we have any questions in the meantime?
Hey, Anthony, this is Rob. How you doing?
Hi, Rob. This is good. How are you?
Good. So one of your slides showed that you have kind of a POSIX way to get at things, an MPI way to get at things, a VFD way to get at things, and a vol way to get at things. Could you sort of reflect on all those different kind of modalities and the advantages and the disadvantages of those in the context of accessing via HDF?
Yeah, that's a fantastic question. So as you are very well aware, the HDF library, it has all of those like layers, right? Like you can do on the API and then within the library, and then it reaches the VFD, and eventually we can do POSIX, right? So first, the POSIX adapters and standard IO adapters are trying to just capture any kind of POSIX workloads and standard IO workloads. By analyzing Argon, actually data traces from the repository you guys have, a lot of jobs are still like POSIX and standard IO, a lot of these things. So that's the fundamental thing. Again, linking to that. Disadvantages, well, you might be careful a little bit of what you're intercepting. There is a way to exclude certain directories or certain paths, so the interceptor doesn't do that and buffer like other things except your application IO. Again, a little bit experience there with the preloading, and for instance, you may be preloading a bunch of libraries, and then you have to make sure that there is an order to that of how which call. Again, there are maybe some solutions. I think Livermore or Berkeley worked on a library that resolves preload dependencies and things like that. So again, suggestions to the community. But on the positive side, everything is transparent. Like you can just run it, and your code is not changed, and it works. And we're happy with the performance we see. On the HDF5 side of things, you can still use the POSIX adapter and leave everything unchanged because the HDF5 library eventually will call POSIX. But we thought it would be even cooler if, and for technical reasons cooler, if we develop the virtual file driver. At that level, really, you don't have a lot of high-level mappings of data structures, like data sets and chunks and groups. Things are getting lost in the VFD, but you do have some sort of a tag or something. This is metadata and this is raw data. So for that, I think it's really interesting to us that we develop the VFD to take advantage of this kind of categorization of what kind of data am I writing right now. And we develop different mapping algorithms for metadata that usually are very small and in different order, like kilobytes or bytes and things like that, to map them to RAM buffer IDs. So we can kind of keep them more in RAM or in buffer collections that they are more organized for smaller IO. And then we have the raw data that just maybe split, kind of like the split VFD that can go to like a different allocation or different tiers or can handle them differently. By managing the splitting of metadata and data at the VFD layer, we actually achieve better performance than just blindly buffer anything out of the POSIX driver. So that was a motivation. And further to that, you could do custom mappings, like say the program is doing chunking or hyperslab selections and things like that. You could be able to develop your own mapping algorithm at the VFD layer that as data arrive, you can map them in the hierarchy differently. Right now, what we use a paging mapping, which is looks at the file and says, here's your page, let's say 1 megabyte page size. So every 1 megabyte becomes a blob in the hierarchy. Anything that lands within these offsets, it will land to the certain blob and it will be mapped to the blob. But I think there's an opportunity to do custom mappings and per workload mappings that can even further accelerate things. In terms of downsides, I don't see a lot of downsides for the VFD. It's just an environment variable. You said it, in the beginning. It just links to that and should work fine. And it does reconstruct the file at the end. So you do have the same output at the parallel file system level. I don't know if I answered the API IO, again, similar logic, right? Just different interfaces. It might be a little more tricky. Like I think, to be honest, to the community, the driver we have, the adapter we have, it's tested and with well-behaved workloads and not a lot of complicated MPI things. But it's a more complicated interface, and so we hope we can develop it even more. It does support all the operations, all the APIs supported. But in terms of tested and scalability, we haven't tested like 10,000 cores, to be honest with you. So we want to do that in the upcoming period, trying to test it more and more and work with partners to try to scale the solution to bigger scales. I hope I answered the question. Do you have any other question on this matter?
Well, I think so. I think you also showed a vol implementation. Is that
The vol implementation is actually ongoing right now.
okay?
I want you to think of the vol we are trying to do not as a bypass of the HDF library and go right to Hermes, because there are vols that redirect the entire thing to something else, which is cool. For us, I think what's important is to kind of maybe capture that higher level understanding of the operations. If I knew a few things there, if I managed to capture some statistics, your data set open could be a trigger for Hermes, like a synchronization point that says, hey guys, we're opening this file, we're probably gonna read it. Do something about it. Kick the prefetchers on and stuff like that. So we wanted to leverage the vol as a hinting mechanism, as a driver of behavior from the program.
Okay.
And kind of like communicate some of these hints and synchronization points to the library down.
So in that case, then you would still probably use the VFD implementation,
Yeah.
but with a little extra information.
Yes.
Okay.
Exactly.
Cool.
That's the idea, and we're developing it right now, actually. So it's like pretty cool.
Yeah.
We have
All right.
more to say.
Thank you.
Thank you for the question.
Sure.
I think we're running out of time. MPI is a Hermes. Okay.
I tried to answer.
Yeah. I was just like, what is this? Do we have any other questions? I'll be happy to take them. Let me see my notes. Do we have any other interesting things for you guys on the questions? How much RAM should I set aside for Hermes buffering space? Again, I answered, I think earlier, configured by the user. Should be 10 or 20% available for Hermes, our recommendation, but it depends on the program as well. What's the footprint of metadata? A few megabytes. Is there any interference between Hermes and OS page cast? Yes. It's a long story, but yes, there is interference. We want to make a little more studies on if you disable the OS page guys and you only have Hermes, or should they work together, and things like that. But yes, prefetching. I know Chris mentioned the prefetching is coming, and the staging in, staging out. I will end the webinar with this kind of future steps we're taking, and I think are very important. I think we think as a group and as a team, and what we hear from the community. So staging in, staging out. And I kind of want to hear also your thoughts from the community about this. Obviously, nothing is free. Moving data from an outside source into your allocation, in this case, Hermes, is expensive. If you try to move a few petabytes of data, it will take some time, right? Because you're reading from parallel file system. So first question is, who is paying for that cost? Is this part of the job? Is this part of the system administrator, like just moving things in and out? Unfortunately, we don't have the power as an independent Hermes library and authors of this library to influence a lot. But I've been talking to the community, and I think what's common across sites is that there have been investments in this kind of better storage mediums, PMEMs and NVMEs, but they're underutilized. And I think the main reason was the lack of software to do that. So we believe that there's an opportunity there that Hermes can come in and manage those hardware, this fancy hardware. And as adding the staging in and staging out capability, I think it will allow the users to kind of have a free mind in terms of using all of this complexity. Effectively, what we're envisioning is you go into your scheduler, you say, hey, here's my Hermes staging job. That will spawn Hermes, the daemon version, into your allocation. It will launch the reading program, the staging in program that you allocate, you tell the program what you want to stage in. Very descriptive. You can be files, it can be part, HDF things, or the whole directory from a folder or something. And then we read all of that into the hierarchy. Of course, we read it and we place it using Hermes library with the data placement engine. Everything is hierarchically distributed everywhere. And then your program can start. Your program ends. You can do programmatically a stage out inside your program if you want to change your program or on finalize, or you can exit the program and then launch the staging out job that will go and evict everything from the Hermes daemons out to your preferred output. So staging in, staging out, pretty interesting things. We will be working now on this functionality. And finally, the prefetching, as Chris mentioned, which it's not the same with staging in, staging out. Like prefetching refers to content already inside Hermes, and we want to we know a read is coming. What can I do to influence the speed of that read? One thing we can do is manipulate the blob composition. Where is the blob right now? It's spread across the hierarchy. 50% of the blob is stored in best buffers. We go in the prefetching phase and we say, well, can I manipulate that and have 80% of the blob into RAM? Because I know a read is coming. So this is a little bit of orchestration between the Borg and how Borg is moving those blobs up and down, and the prefetching. So the prefetcher will be this trigger, this engine that kind of manipulates the blob composition. And with that, if we don't have any other question, I will end the webinar here. Thank you all for attending. Again, content will be available online. Please check out our GitHub. Please, use any of this community infrastructure we have set up. And feel free to contact us at any time. If you have a use case or a program or a problem with data movement, data sharing, IO being slow, we're here to help. Thank you all for attending. Enjoy the rest of your day and the weekend.